Welcome back. So far we have discussed the back surface field and the Pearl-PERC concept. The back surface field and the Pearl concept was traditionally based on a p-type wafer. However, we have to note here that n-type wafers have favorable electrical properties over p-type wafers and are therefore gaining a higher fraction of the market over the historically favored p-type wafer. In general, the minority carrier diffusion length in n-type wafers is much larger than in p-type wafers since it has fewer metallic impurities. Secondly, n-type wafers are not sensitive to light-induced degradation. In p-type wafers, simultaneously boron and oxygen are present, which under light exposure start to make complexes that act like defects. The light-induced degradation causes a reduction of the power output. Therefore, currently, boron p-doping is replaced by gallium p-doping. However, all these effects are beyond the scope of this course. But the upcoming cell concepts we will introduce here make use of n-type wafers, such as the next device concept I will discuss, TOPCon, the tunnel oxide passivated contact solar cell. Here you see an illustration of the TOPCon cell. We can see that the front surface processing is more or less similar to the PERC and Pearl solar cells, but where we previously introduced localized contacts with a back surface field to reduce recombination at the back contact, in the TOPCon solar cell we see a different solution. In order to prevent the minority carriers to recombine at the back contact, a very thin oxide layer of approximately 2 nanometers is placed in between the n-type base and a phosphorus-doped N+ layer. The band diagram of the back contact demonstrates the principle. Left side is the N+ layer and the right side is the n-type crystalline silicon. Now, since the oxide layer is present, it is almost impossible for the minority carriers, which are holes for the n-type wafer, to reach the back contact of the cell, as they cannot pass the potential barrier introduced by the oxide layer. In addition, you see in this example that the electrons experience a smaller barrier than the holes. In contrast to classical mechanics, in which a particle cannot move through such barrier, in case of quantum mechanics, this is still the case, since this oxide layer is kept very, very thin. A large fraction of the electrons can move through this barrier, and this phenomena is called tunneling. Therefore, electrons are able to tunnel through the barrier and be collected at the back contact with virtually zero loss. Contact patterning, which is a relatively difficult and expensive processing step, is therefore not necessary, and the backside of the wafer can be entirely metallized, making this technology cheap in processing. An alternative concept with high efficiency is the so-called crystalline wafer-based heterojunction solar cells. The heterojunction solar cell is shown in more detail in this illustration. First, I have to answer the following question: what is a heterojunction? So far, I have introduced you to the concept of PN junctions with a depletion zone. These junctions are fabricated by different doping types within the same semiconductor material. This means the band gap in the P and N dope material is the same. Such PN junction is called a homojunction. However, you can also make a junction by two different semiconductor materials. For instance, one semiconductor material that is p-doped and another type of semiconductor material that is n-doped. This is what we call a heterojunction. In the crystalline silicon wafer-based heterojunction, we make use of two types of silicon-based semiconductor materials. One is again an n-type float zone monocrystalline silicon wafer. The other material is hydrogenated amorphous silicon. This is a silicon material in which the atoms are not ordered in a crystalline lattice, but in a disordered lattice. Next week, we will come back to this material when we are discussing thin film PV technologies. For the moment, you only have to know that this material has a higher band gap than that of crystalline silicon. Secondly, amorphous silicon can be n-doped and p-doped as well, using phosphorus or boron. I won't go in detail, that is out of the scope of this course, but the electronic band diagram of an heterojunction of an n-doped crystalline silicon and p-doped amorphous silicon in the dark and thermal equilibrium will look like this. You see that next to the induced field due to the space charge region, some local energy steps are introduced. These steps are caused by the fact that both band gaps are not the same. At this junction you see that the valence band is higher positioned in the p-type amorphous silicon in reference to the n-type crystalline silicon. This will allow the minority charge carriers, the holes, to drift to the p-type silicon. However, you see in this example that the holes experience a smaller barrier. A large fraction of the holes can move through this barrier by the earlier mentioned quantum mechanical phenomena of tunneling. Now look at this crystalline silicon wafer-based heterojunction solar cell. This is a concept which has been invented by the Japanese company Sanyo, which is nowadays part of Panasonic. The Panasonic cell is called the HIT cell, which stands for heterojunction with intrinsic thin film. The heterojunction cell configuration has two junctions. The junction at the front side is formed using a thin layer of only 5 nanometers of intrinsic amorphous silicon, which is indicated by the red color. A thin layer of p-doped amorphous silicon is deposited on top and here is indicated with the blue color. The heterojunction forces the holes to drift to the p layer. At the rear surface, a similar junction is made. First, a thin layer of intrinsic amorphous silicon is deposited on the wafer surface indicated by the red. On top of the intrinsic layer, an n-doped amorphous silicon is deposited indicated by the yellow color. As discussed earlier, for high quality wafers like this n-type float-zone monocrystalline silicon wafer, the recombination of charge carriers at the surface determines the lifetime of the charge carriers. The advantage of the heterojunction solar cell concept is that the amorphous silicon acts like a very good passivation material. In this approach, the highest possible lifetimes for charge carriers are accomplished. The crystalline silicon wafer-based heterojunction solar cell has the highest achieved open circuit voltages among the crystalline silicon technologies. Panasonic and Kaneka achieved an open circuit voltage of over 750 millivolts. How do the charge carrier travel to the contact? The conductive properties of the p-doped amorphous silicon are relatively poor. In the homojunction solar cells, the diffusion to the contacts takes place in the emitter layer. In contrast, in a heterojunction solar cell, this occurs through the transparent conductive oxide material like an ITO, which is deposited on top of the p-doped layer. The ITO is needed as the conductivity of the p layer is too poor. This results in such small diffusion lengths that the practical metal finger spacing cannot be achieved using the p layers. Therefore, the ITO is used. An advantage of the heterojunction solar cell concept is that it allows to introduce the same contact scheme at the n-type backside. It means that this solar cell can be used in a bifacial configuration. It can collect light from the front and scatter and diffuse light falling on the backside of the solar cell. An important advantage of the heterojunction solar cell is that the amorphous silicon layers are deposited using cheap and straightforward plasma-enhanced chemical vapor deposition technology at low temperatures, not higher than 200 degrees Celsius. This means that making the front surface and the back field in this type of solar cell is very cheap. Furthermore, this technology allows to use the N-type wafers. In the next video, I will introduce some contact architectures like interdigitated back contacted and metal wrapped through solar cells. So, see you back in the next video.